Hi, I'm Alexander Suh from Wayfair Research, and I'll be presenting a new way to use bug prediction models to help developers. So before we talk about actually predicting reverts, get a bit of background out of the way about what a revert actually is. So recall that in Git, we can undo changes made in a commit, and we do this by creating another commit called a revert. The revert basically just undoes whatever the first commit did. It deletes whatever the first commit added, it adds whatever the first commit deleted, and so on. And developers use reverts for all sorts of things. You might use it for a hotfix, you might use it to clean up some code, uh, but in a lot of large-scale continuous deployment processes, like Wayfair's, reverts are used to remove bugs from the deploy process. So what does this look like in practice? Well, generally you'll have a deploy pipeline that starts with developers testing their code and then having that code reviewed. When a developer is ready to deploy their code to production, they submit their code to a queue, and engineers managing the deploy process will take code off of this queue, say 50 commits at a time, and when they're ready to deploy a batch of code to production, they'll take these 50 commits and they'll try to compile the code in what's called the build stage. And if the build stage goes as planned, then they'll take the code and put it on a staging server where they do a last few checks to make sure that no errors are being introduced. And if all looks well in staging, then everything gets deployed to production. And if there are no bugs in production, then all is well, and the engineers managing the deploy process can move on to the next batch of, say, 50 commits. But what if everything doesn't go as planned? What if the deploy process does encounter a bug? Well, let's say that we encounter a bug in the build stage. Then the engineers managing the deploy process have to figure out which of the 50 commits that they were trying to compile is actually causing this bug. And once they figure out the offending commit, they can revert it and then try again with the other 49 commits. So let's say that they figure out which commit was causing the error in the build stage, and they move on to staging. And staging goes as planned, and they move on to production. But then let's say we find an error in production. Well, then the engineers managing the deploy process have to find which of these other 49 commits is causing a bug in production. And when they do, they'll revert that commit and try the whole process over again with the remaining 48 commits. And as you can imagine, this process can take a lot of time if there are a lot of bugs in the deploy process. At one point in Wayfair's history, it wasn't uncommon for deploys to production to take over an hour because engineers would find really confusing errors during the deploy process and would have to figure out which commits to revert. And you can imagine that that's really costly, not only because you're wasting developer time, but also because if the deploy process takes longer, it can mean that certain features don't get out on time. It can mean that certain hotfixes are delayed. And so it is quite important that the deploy process goes smoothly. So researchers have taken an interest in finding ways to speed up this process by helping developers find and remove bugs from their code. And one way to do this is with bug prediction models. A bug prediction model, when given a piece of code, say a commit, tries to predict whether that piece of code will be buggy or not buggy. And the idea is that if a developer could be told when their code is buggy and when it isn't, then this could help developers test their code and also help developers do code review so that buggy commits wouldn't even get into the deploy process in the first place. Unfortunately, that's not what tends to happen in practice. You see, a bug prediction algorithm can usually only tell you the likelihood that a commit will be buggy. It can't tell you why the commit is buggy or how to fix the bug. So previous studies haven't found any measurable change in developer behavior when using bug prediction algorithms, largely because the information they provide hasn't been very actionable. On top of that, there have also been a lot of issues in the past with how bug prediction models are trained. To create training sets for bug prediction models, researchers have typically relied on commits labeled as bug fixes in commit history. So for example, if there is a commit A that modifies files X and Y, and then later on, the next file the next commit to modify file X is commit C, and commit C is labeled as a bug fix, then it's assumed that the bug fixed by commit C was introduced in commit A, and so commit A will be labeled as buggy. And by labeling commits as buggy or non-buggy in this manner, uh, researchers can train classification algorithms to predict whether any given commit will be buggy or not. And this approach to creating training labels might seem plausible, but in practice, it leads to a lot of commits being labeled as buggy that aren't really the kinds of buggy commits that developers are really looking for. For example, previous studies have found that datasets used to train bug prediction models often contained commits labeled as buggy, where the corresponding bug fix didn't happen until months or even years after the buggy commit was actually introduced. And this suggests that a lot of these commits labeled as buggy are actually very trivial bugs that developers don't really care about, since they didn't bother to fix the bug until months or years after it was first introduced. So at Wayfair Research, we wanted to create a model that would help our developers find and remove bugs during the deploy process, but we wanted to make sure that these models would A, deliver actionable information, and B, that they would predict the bugs that developers actually cared about finding. And our approach to this was to have our models trained to find specifically those bugs that are reverted during the deploy process. This way, if an error were to occur during the deploy process, and engineers had to figure out which of 50 commits to revert, our model could be used to tell engineers which commit caused the error, or at the very least, which commits were more likely to cause the error, so that engineers could examine the commits in order of most likely to least likely to have caused the error. So how did this work in practice? Well, we used 6 months of commit history from the main Wayfair codebase to create our training set. And to create the training labels, rather than basing our training labels off of bug fix histories, we based them off of reverts on the main branch of the Wayfair codebase. Because recall that if you're reverting on the main branch, the chances are that you are reverting an urgent bug from the deploy process. And this is something that we manually verified as well. In a set of 50 reverted commits that we manually inspected, we found that 46 were actually reverted due to errors found during the deploy process, and 4 were related to things like, say, someone deploying a change to a feature and then deciding they like the old version of the feature better. So it was pretty safe to assume that if commit A was deployed to production and then immediately reverted, that revert was due to commit A introducing an urgent bug that had to be removed in the deploy process. Of course, it is possible that when engineers are trying to revert the source of an error, they'll make a mistake and they'll revert the wrong commit. And in these cases, the typical response is that if you revert a commit and then later on find out that it wasn't actually the source of an error, that you'll just revert the revert. And by reverting that revert, you'll allow the first commit back into production. So when creating our training labels, if a commit was reverted and then the revert was reverted, then ultimately that first commit ended up not being reverted, and so we would label it as not buggy. So having established a method to create labels for our training data, we then turn to deciding what features and what classifiers to use. For both features and classifiers, our approach here was pretty similar to what previous bug prediction algorithms had done. On the side of features, we experimented with change metadata, which is the metadata on commits that you can scrape from commit history. So that's things like the number of lines changed, the date of the commit, stuff like that. We also extracted features from the actual text of the commits using a fairly standard bag of words approach. So we used bag of words to extract features from the commit messages, from the file paths of the modified files, and also from the code changes themselves. And between change metadata and bag of words features, these were really the features that we focused on for our experiments. Complexity metrics, those are things like the number of linearly independent paths through a program's source code. We investigated those briefly, but because the code base we were working with was built in PHP and JavaScript mainly, and there simply weren't any good libraries to collect complexity metrics for those two programming languages, so we ended up omitting those from our features. As for abstract syntax trees, these are similar to the language trees you see in natural language processing, but instead of using a tree to express the semantics of a natural language sentence, you're using a tree to express the grammar and syntax of a program written in a programming language. And researchers have developed a few methods to extract features from these abstract syntax trees. For example, using neural networks to learn embeddings on them. But for our purposes, we ended up not using these features because we simply found that they took too long to compute. Computing features on abstract syntax trees often took several minutes or more, especially for larger programs. And that just wasn't fast enough for us. You can imagine that if you're a developer looking for the source of a critical bug, uh, you really want to get answers from our model just simply in a shorter amount of time. And so we ended up omitting those features from our experiments as well. As for classifiers, previous bug prediction studies have used a really wide variety of classifiers, everything from linear regression to support vector machines to neural networks. You name it, it's probably been used. For our purposes, we focused on gradient boosted decision trees, support vector machines, and k-nearest neighbors. And part of the reason for this was that A, these had done well in previous studies on bug prediction, but also B, at this point, through user testing, we were starting to realize that rather than just simply giving a prediction of whether a commit was buggy or not, what would be more useful to developers would be to give them a ranking of commits in order of likelihood of being reverted, so that engineers, when looking for the source of an error, could inspect more risky commits before inspecting less risky commits. And all of these methods are capable of doing ranking in some manner. And so it's why we went with these methods rather than a classifier like, say, naive Bayes. So in the end, we found that using change metadata features with a gradient boosted decision tree yielded the best results for us, with a very respectable AUC of 0.76. And that's the model that we ended up using to build a tool for developers at Wayfair. So what you see here is the control panel that engineers in charge of the deploy process use to manage deploys to production at Wayfair. On the right-hand side of that control panel, you can see a list of code changes that developers are requesting to be deployed to production. And if there is an error during the deploy process, the engineers in charge of deploys will go down that list and inspect those commits to try to figure out where the source of the error is. In this version of the control panel, you can see highlighted in yellow sorted by merge order, which basically means that the commits in this list are essentially sorted at random. They're really sorted in the order that they appear in the database, which is basically random. And so, as one might expect from a random ordering, a reverted commit on average would appear about 50% of the way down that list. On the other hand, in this version of the control panel that makes use of our algorithm, you can see that the list is now sorted by the estimated probability of a commit being reverted, where commits that are more likely to be reverted are on top. With this new ordering, reverted commits didn't appear 50% of the way down the list. Instead, they appeared 20% of the way down the list on average. And so engineers could trust that reverts more likely to be reverted would show up earlier in the list. We then manually timed engineers in charge of the deploy process to see whether this new control panel actually measurably decreased the time it took for them to find bugs. And we did find that there was a 55% drop in time to find non-trivial reverts. Non-trivial meaning that the source of the error wasn't immediately obvious to begin with. When surveying engineers about the usefulness of our algorithm, we also got fairly positive qualitative reviews. One question we asked was, on a scale from 1 to 10, how helpful are the revert predictions in deciding which deploy requests to revert? And the mean and median response to that was a 7 out of 10. And we think that a big reason that developers found this model's predictions to be actionable and actually helpful to them was that introducing this algorithm didn't require them to change their workflow at all. Before we introduced the algorithm, the engineers would go down their list of deploy requests on the control panel and try to figure out which one was causing an error. And after we introduced the algorithm, their workflow was exactly the same. It's just that the list was sorted in a different order. That being said, there were some challenges in introducing our algorithm to engineers. In particular, we originally told them that this was a revert prediction algorithm, and phrasing this as revert prediction often caused engineers to trust the algorithm a bit too much. Rather than inspecting commits in a different order as we intended, engineers would sometimes just assume that commits toward the top of the list were buggy without actually inspecting them, which of course is not what we wanted. So instead, you can see that we ended up phrasing the output of the algorithm as an estimation of revert risk, which worked a lot better in getting engineers to use our algorithm as intended. But all in all, we're quite happy with how this algorithm performed, and it's still in production today. And I hope that you've enjoyed this presentation. Thank you.